Let's continue the neural network structure. So eventually our object, the goal is to condense this structure into this form where the x is the input. The input is x1, x2 to xn. Output is y1, y2 to yn. So input is x, and this is the neural network, and that equal to the output. Input x, output y. W and v are the weight of each link. W and v are matrices. Each element of the matrix represents the weight of one link. And we say here's inputs. Each one represents the input value. And the input x1, for example, it times some weighting v11 where it goes into the first neuron. But that's not the only input of the first neuron, right? The other input might be from the second input. x2 times v12 will be another input to this neuron. So it's 1, 2, and some others. And this, it also includes one offset input, or someone calls it bias. So this is a constant, and it's a weight. It's still, you can consider to be a weighting. Okay? It's a constant, and it's a weighting term to be estimated. And that goes into a neuron, okay, represents some offset from 0. From the so we call this hidden layer, output layer. So from hidden layer to output layer, the operation is similar. We have inputs from different neurons. We have one input, another input from the offset. Okay, again, it's another weighting to be estimated. And combine those, put into the neurons that generate output. So now what we're trying to do is, given this, I want to give you how we can convert to equation 4. First, input layers. So from here, the input to the first neuron is theta v1, right? Theta v1 times this, all the way down to the xn, right? So it's the offset term times x1 plus x1 times the weighting v11 plus x2 times the weighting v12, right? All the way up to xn v1n. So this can be represented as a summation of variable k from 1 to n, and v1kx, k is the variable, plus theta v1. And input to neuron n, input to this neuron can also is similar, right? And it can be Vn plus x1 bl1, okay, L, which is the weightings from here to here, okay, plus x2 vl2 plus plus xn vln. So again, it can be condensed down to this form. The only difference compared to the first neuron 1 is this subindex. Here's a 1, here's L. Okay? So I just keep this, erase this. Okay. Next, here's input layer. Now we consider neuron layer, and it's straightforward to interpret these layers. Okay, so for neuron 1, you put the input into the sigma, right? For neuron 1, this is the input to the first neuron, okay? Input to the first neuron, which sigma can be, for example, this function. This is one of the nonlinear operation in a neuron. Just one of those, can be other forms. So this gives an output. The result of this is the output from this neuron, right? And that will go into the upper layer. So upper layers. For example, y1. How we get y1? Y1 is you multiply the output from the first neuron times W11 plus output from this neuron times W12 plus all the way down to here and the offset term, right? W11 sigma this, right? From the first neuron. And this, okay? VLK XK plus theta VL. Okay? Here are L terms plus offset. So this is the output 1, which is Y1. Y1 is equal to this. Okay? For YI, it narrows down to what? You see 1, right? And here is subindex 1, 1, 1, right? So if for yi, you can replace this one by I, this one by I, this one by I, right? Y1 is equal to summation of j equal to 1 to L, because here are one term until L terms. So you can summarize the first L terms and put the j variable index into here, right? The second element, sigma. Another index is this term, this index, right? This index, this index. Okay, so let's n k equal to 1. V j k x k plus theta v j. You just replace j by l. Replace a by j, l by j, right? Here and here, and plus theta w1. Okay, 对吧？ Vj xk vxk jk ij. For yi, you can replace. Here's 1, right? And here's another 1, subindex 1, another 1 here. You just replace 1 by I. Okay, for yi. I stands for 2 until 1, 2 to m. Okay. So yi equal to L, j equal to 1, W, I, j, sigma, n, k equal to 1, vjk, xk plus theta v, j plus theta w, I. This will be same as how we have in the paper. same as this. The equation 1 is the same as equation 4, except here's the one element of that y column. Okay, so why they are equal? You can consider in equation 4, the v is the weighting. Okay, v is a matrix in which every element of v is the link between input layer to hidden layer. This is x, right? X on the equation 4, okay, times vt. We say this is vt, okay, for example. And what is vt? We know the first row of vt will do the inner product with x and generate the first element on the column of this column vector, right? You can observe if this is this value is the input to the first neuron, okay? What this value should be? It should be the weightings of this one, this one, this one, right? All the weighting between these two layers, and that mapping from the input to the first neuron. Because your x1 times v11 is the input to this. x2 times the weighting v12 is the input to this neuron. x1 should times v11. x2 should times v12. All the way up to v1 n. Okay, that will be the input to the first neuron. And remember, we have offset. So if you put offset in the x, you put 1, and here it should be theta v1. Because theta v1 can be considered as another parameter that to be another weightings to be estimated, right? So here's the estimate value, estimate constants. So we put all the estimate in this matrix V, okay? So this is the input to the neuron. Input to the neurons. Okay, this is Vx. And Vx will be the argument for the activation function. That means that all these are the input to the neurons. So that gives you, after you do the operation, this is the output from the neuron. Right? The output from the neuron will also again combine with the weighting matrix W and give the output. From the output, this guy should times WT, another weightings. Okay. The output to the neuron times the second layer weightings will generate the output, which is from Y1 to Yn. So here the dimension should be the number of neurons, which is L. Okay. And here should be L plus 1, L plus 1, because this is from the offset, And that generates the output, and the dimension is M, because it's Y1 to Yn. Yeah. Okay. So V and W are the weighting matrix to be estimated. This neural network to help us to Y transpose theta. We use Y transpose theta to replace some of the dynamics, right? For example, so originally MR might be MQ. Okay, originally the open loop dynamics can be this. and assume that this is linearly parameterizable, right? We can narrow down this equation into y transpose theta. Y is the regression matrix, theta is the unknown parameters. Then the control design will be easier, right? We can design control that is y transpose theta hat plus or minus kr. Okay, feedback and the estimate, which can be considered as a feed-forward term, right? Now, if you have neural network, with neural network, you can say, okay, MR, now I want to approximate this function by another F, okay, by another neural network. Now you use neural network to replace this. What's the advantage? You already have this, right? You already learned this. But why you still learn this? Because there's a constraint about this. Linearly parameterized. This structure had to be linearly parameterized. But there's no constraint on NN. There's no constraint on this. So if you cannot do linearly separated for the dynamics, you can use this. So assume we say it's f, another nonlinear function. We assume that f, this f can be this structure. Okay. Can be a neural network function. And this function is used to approximate a nonlinear function. But remember that we say from last time that the neural network cannot truly represent the function. It can only approximate the function. Okay, it approximates the function with some error. And this error can be reduced by increasing the number of neurons or the number of hidden layers in this neural network. Okay, so you cannot truly use the neural network to replace the function. You can only approximate. Now we can replace f by okay. And again, this is the true weight, the true weightings to approximate this f. These weightings are unknown. Same as this theta is unknown, right? We need to estimate the theta. So again, to estimate this function, we need to design or rewrite this into this form where the W and V are the estimate weighting. This W hat, V hat are the estimate of W and V. The estimate error can be defined as the true weighting minus the estimate. The difference in the output of the activation function is the difference with the true V value and the estimate V value as an argument of the activation function. How can we use this neural network to, for example, in the ordered Lagrange systems? So given these dynamics, we can define another function, nonlinear function, which is a function of the desired trajectories. Okay. Given this open loop dynamics, okay, we can define another function, auxiliary function, nonlinear function. That's a function of the qd dot. And that function is dynamics. It's this dynamics Okay, but it's along the desired trajectories. We replace every q double dot by qd functions. Because in here, to do an approximation on the nonlinear function using neural networks, the variables has to be the input x is restricted to a compact set. Okay, that means you want to use neural network to approximate a function. The variable x has to be bounded. Compact set means bounded. Compact set means x has to be bounded. But here comes the problem, right? X is the state. How we can show that before proof x is bounded? No, right? So that's why we here design an auxiliary function that is a function of desired trajectory, because desired trajectories are bounded, are in a compact set. Desired trajectory is a user-defined function, and you don't want to design a function that is unbounded as a desired trajectory, right? So we already know that qd dots, qd double dot are bounded, and therefore that will meet this constraint. Okay. Then we can use a neural network to approximate this FD function. Shown that as long as x is restricted to a compact set S of Rn, S is a compact set, means that every x has to be in this S set, and if it's in S set, every x is bounded. Input of the neural network has to be bounded. Okay, that's why we designed this FD. So with this FD, we can rewrite this dynamics before filter tracking error. E1 equal to the tracking error. E2 is E1 dot plus alpha 1 E1 E, and R is E2 dot plus alpha 2 E2. Okay. Then we can rewrite this as M QR plus equal to FD plus S plus tau D minus S minus tau. Okay, FD is the FD. S is okay. So now we use FD, the auxiliary function, which is defined as this, to replace some of the open loop dynamics on the right hand side. Okay, replace some of the dynamics. And S is the terms that include the mismatches for F, for G, for VM, and M terms. So this S can be upper bounded by some function of error. And this FD can be approximated by neural networks. So eventually, the control is designed as this. The control is designed as FD estimate plus mu. And mu is a feedback term, okay? So mu D is the approximate of this. FD head is the approximate of this FD, and this is the estimate from the neural network, okay? This is a neural network. V hat and W hat are the weighting matrix you need to estimate. And the adaptive law for V hat dot is a projection function, gamma 1 sigma hat prime V hat transpose xd dot E2 transpose. Okay. E2, okay. W hat E2. Okay, these are the adaptive law for this weighting matrix. Projection function is a function that used to upper bound to prevent this V hat is unbounded due to this adaptive law. In this example, if V hat, the V hat is obtained by integrate this V hat dot, and you find that V hat will go up until you set up a threshold. If V hat is go beyond this threshold, you will constrain V hat dot to be 0, so it will remain constant, remain on the boundary. Okay, so V hat will never go beyond this value. This is the purpose for designing projection function. So if you look at this controller design, remember what's this? It's very similar to this structure, right? You compare the two. Here we use adaptive law, right? And you require dynamics to be linearly parameterized. Here, there's no constraint on the dynamics. We just design a neural network, estimate the neural network to approximate FD function, okay? Because this is approximate of FD function. Okay, and some feedback. And of course, to design this feedback, it requires a lot of effort. So you can imagine that if you use neural network, you update V dot and W dot until this function can truly approximate FD. That means you learn the dynamics, right? You use this to learn the dynamics FD. And FD is what? Is the dynamics. Is the dynamics of this, and this along the QD trajectories, right? The dynamics along the QD trajectories. That means that if you put that in the control input, that means you are on the right track. You generate output that is truly required because it's the approximation of the desired trajectories. FD, right? You observe FD, which is the dynamics along the QD trajectories. And if they are the same, you are generating output that is truly required. And mu is just a feedback. And mu only exists if you have error to be compensated. But if FD hat is truly equal to FD, this term will be 0. You are generating output that's truly required. Remember, observe this, okay? This is adaptive law for V. So if this part, if this is always positive, V hat will keep increasing, right? V hat will keep increasing, okay, if this is positive, okay, because V hat dot is positive. So projection of this is that you set up a threshold for V dot. If for V hat, and if V hat go beyond, is on the threshold, okay, and try to go beyond this threshold, you will keep this V hat at this value, which is the maxima value for V hat. Is the upper bound for V hat. Okay, you don't let V hat to keep increasing. So you project the value back to this boundary. V hat equal to this. Okay. If this is the threshold, okay, some boundary. If it's less than the threshold is in the boundary you are safe, then we use this adaptive law. V dot equal to this adaptive law. Otherwise 就是说，如果它在这个线 if it's on the line or beyond this region, the v hat that will be 0. It's stop doing integration. The value will hold a constant. V hat will hold a constant. The reason I told this is for you to have what is neural network, what we can use neural network in our control. Later, sometime in your research, you need this solution. You can go back to check out this. I don't hope you to understand this in a short time, like one class. No, I just give you a broad introduction. Just keep in mind that this is the takeaway, okay?